I will begin with a word of prayer. Heavenly Father, we thank you again for your many blessings. We pray that you'd guide our steps today, help us to understand a little bit more about magnetism. In your name I pray, Lord Jesus. Amen. So I mentioned to you guys a little bit last time that I had become aware of the issue that magnetic field lines don't always come in closed loops, despite the clear declaration of such from many physics textbooks, right, especially introductory. And I've been trying, as I told you guys before class, to find a decent, simple example of this. And so far that has still eluded me. But Dr. Schmidt sent me a copy of this paper by Luca Zilberti entitled The Misconception of Closed Magnetic Flux Lines. He's an Italian. This was published in March of 2017 in IEEE Magnetic Letters, Volume 8. And I'd just like to read like a paragraph or two from it. It says, many textbooks support the idea that B field lines are always closed, or at most extend to infinity. Among them, we may mention those by Stratton, 1941, Morse, 1953, Sommerfeld, 1964, Weber, 1965, who associates closed lines with a solenoidal vector, Paul, 1982, and Griffiths, 1999. The last being most relevant to me. See, because Griffiths, 1999 is what I studied when I was in your place. And that is why, forever ingrained in my mind, was magnetic field lines are always closed loops. Well, Griffiths, circa 2025 now, has seen the light. And now he has a page where he admits otherwise, right? He says, one of the earliest discussions about non-closed magnetic flux lines was given by Nobel laureate I.Y. Tam in his book published in Russian since 1929. He analyzed the field produced by a straight wire in a circular concentric loop, which will be further analyzed below, blah, blah, blah. Anyway, so this paper, it has, some pictures. I haven't had a chance. I just got this a couple hours ago. I haven't had a chance to digest it, but it apparently has like a picture of a loop and some, But I don't see any equations in here which just jump off the page at me like, oh, that's a simple example. So my quest continues. I mean, this is confirmation that, that your current edition of Griffiths is not wrong, right? But I'd like to find a simple, if you can find a simple example, it would be worth 30 points probably. Yeah. Okay, so let us get back to business. So we're talking about the magnetic vector potential, right? And so we've been talking about the vector potential, right? And just to remind you guys, what we found was that we could say A, and he ultimately he gave us a few different things. Like you could say A of R is mu naught over 4 pi is the integral of the current density at R prime divided by the separation distance script R between field point and source point, and then d tau prime. Of course, this could also be in the context that you just have line currents, right? If you just have linear currents, then you could rewrite that as mu naught over 4 pi. Why on earth did I have an alarm set for now? That's weird.
Is that a 2-minute alarm?
I have no idea what that is. It must be from like another class. It must be from like my, anyway, who cares? Integral, sorry about that, of I over script R dl prime. All right, we'll actually come back to this one a little bit later today if I do my job. All right. Anyway, the point of all this was we can get the magnetic field as the curl of the vector potential, right? So this is how we find the magnetic field. And if we have the vector potential, we take its curl, we get the magnetic field. And we even looked last time at the rather quirky idea of a magnetic scalar potential, and I explained to you why that could only be possible in a very particular context, right? So a couple things I wanted to do today. One was to work out the example of the spinning charged ball on like section 5.1 in Griffiths. But the other thing I wanted to do was just a little bit more adventurous, which was to see if we could find the vector potential for the Coulomb field. This is a really weird idea. So example one, this is a little bit adventurous, but you know, we had that the, suppose we have B equals to, and it's not the case, right? But suppose we had r hat over r squared. And I'll avoid any, it's dimensionally nonsensical, but let's just suppose that for a second, okay? So this would be the monopole field, right? Because the divergence of B would be what? What's the divergence of r hat over r squared? We've talked about this before, right? It's 4 pi, you know, right? So I guess to give us the monopole field, I guess I should really do like, I'm just going to leave it like this. Of course, I mean, you could divide by 4 pi or something so that you'd have unit magnetic charge if you wanted. I'll tell you, I'll do that. It's bothering me. I'm just going to do that. Slightly more physicsy. You happy? 4 pi r squared there. Now this would give us, you know, there we go. That would be sort of ignoring some dimensional stuff, just the unit monopole field, right? So what's the vector potential for this? Is my question. All right. Can we find a vector potential? Now Shane has already thought about this because he had the misfortune, you know, of taking my. Now I'm going to delete the 4 pi now, if you guys don't mind, because I'm already tired of it. Can we? Oh, good gracious! That's not what I mean. I really wanted to teach this class, but I really don't want to teach this class after I've taught 3 other classes. I'm grateful I'm teaching it, don't get me wrong. All right, so A. Can we find A such that that's the case, right? Such that this is equal to r hat over r squared. Now, I want to suggest that we just combat this directly by using the formulas on the cover of Griffiths. And let's see if we can find our way through. Because in the cover of Griffiths, we have the formula for the curl in sphericals, right? So like, what is the curl of A in sphericals? Look it up, right? It's 1 over r sine theta, parentheses, you know, partial theta of, you know, sine theta times a sub phi, right? Minus partial a theta, partial phi. This is all the r hat component. Then next up, 1 over r, 1 over sine theta, partial ar, partial phi, minus partial r of r a phi, theta hat. All right, plus 1 over r, partial r of r a theta minus partial ar, partial theta phi hat. That is what we're up against. But don't be afraid. We can do it. We just need to think about it. Like, what are we trying to do? We're trying to put this equal to what? We're trying to put this equal to r, right? R hat over r squared, right? So what that means is that all of this, right, has to work out to 1 over r squared, right? This has to work out to 0. And this also has to work out to 0. So my suggestion is that we pick the simplest possible thing and make it work and then go from there. So I think the simplest possible thing would be for this to just be equal to minus 1 over r sine theta times partial a theta partial phi. Right? That would give me like, you know, minus 1 over r equal to partial phi of a theta over sine theta. That is not what I did. Ah, phooey. I worked this out yesterday, guys, and I got it to work. I feel like I'm going down the wrong path. All right, I think it took, all right, so that gives me partial a theta partial phi equals to like minus sine theta over r, right? So I just put that over there and solve for this, which then suggests to me that a theta is just equal to like minus phi times the sine of theta divided by r. So my conjecture is that I can just make A equal to minus phi times the sine of theta divided by r times theta hat. So I'm conjecturing at the moment, right, that we can put like the a sub phi and a sub r equal to 0, right? So this one, if a sub phi and a sub r is 0, we're good, right? A sub phi and a sub r is 0. This is good. This is troublesome. So why is this 0? What's my A theta? See the R's? They'd be canceling. And that was the only other possible troublemaker. So 0, 0. This does what we want it to, and this is 0. There you go. See, if you'd known the spherical frame on that advanced calculus test, you could have solved it like this. I just gave it to them in Cartesians. It was an unfriendly question. Yeah. What does this look like in Cartesians, though? So we've got A is equal to minus phi sine theta over R. Theta hat. Well, anyway, let's not let's not do that. Like, it seems like we found a nice answer, so let's just let it be. All right. But in order to like convert that to Cartesians, I'd have to go and swap out my theta hat for cosine x hat minus cosine sine y hat, the z hat term, and then convert this all to, what's the deal for us? X is equal to r cosine phi sine theta, is that right? That's our spherical, physics spherical, right? You guys got to keep me on the straight and narrow, otherwise I'll slip back into my mathematical ways, I just wanted to point one thing out about this formula before we leave it, because there's something interesting here. So, theta hat's just a unit vector, right? But actually, that's probably where the interesting part is. Golly, this is not what the solution looked like in advanced at all, is it? I don't think this looks at all like the solution we found in advanced. It's interesting. I'm trying to think of how to put that into Cartesians, So like I could say golly. So like tangent phi is equal to what? Y over x, right? So you could do like minus inverse tangent of y over x. The sine of theta, goodness.
Do you want the definition?
Sine of theta?
Or do you want the definition of theta, I guess?
Oh, what do you mean?
Well, it's inverse tangent of root x squared plus y squared quantity over z.
Oh, sine of, what do you say, inverse tangent of what?
Root x squared plus y squared.
Uh-huh.
Quantity over z. Clearly.
Okay. And divided by, of course, the square root of x squared plus y squared plus z squared, right? All of that times the theta hat, right? So, all right, let's stop and take stock of this formula. Parts of it are completely unsurprising, right? Like, all right, so there's something hidden in the theta hat, right? So where is theta hat not defined? Yes, but also?
Z
No. X and Y both 0. The z-axis. This is the place where theta hat not welcome. Not welcome here, all right? What direction does theta hat point on the z-axis? Think about it.
Directly up.
Directly up? No, I mean, the answer is undefined.
No.
Okay, if we look at it. So you can, I don't know if you can quite see that from, I mean, that's hidden in here, right? Now in your face is the fact that x equals to 0's got, like this can't deal with x equal to 0, right? So this vector potential, it clearly has problems other than just the origin. Think about the Coulomb field. The Coulomb field, we don't think about it much. What am I talking about? We think about it all the time. But this is minus the gradient of 1 over r, right? So your potential, I seem to have lost all my units. 1 over 4 pi epsilon, right? 1 over r. I'm feeling guilty for not putting units in, but fine. Maybe I should put a charge in while I'm at it, you know. There. Now we're all physical. It's good. I should be physical. It's a physics class. But so look, the potential is defined everywhere except where the charge is located, right? This vector potential has problems on the z-axis and in its current formulation where x is equal to 0. Those are not physical singularities. The magnetic charge is just at the origin. But the magnetic potential, the vector potential, has singularities at places where there is no charge. All right? There is a way to write this, and I'll do it. I didn't have time to prepare for today. I'm sorry, guys. But like next class, I'll show you Dirac's formula for this. And Dirac's formula for this, the so-called it's the so-called Dirac string. He writes down a vector potential for the monopole, which is only singular on the positive z-axis. And it turns out this is unavoidable. There has to be a singularity in the vector potential. The reason for that is this. If you have, on the one hand, the integral of the monopole field, the flux of it around the sphere, right, is equal to, 1 for my current, putting the 4 pi back in, right? The unit monopole. You have that on the one hand. Suppose you also had a vector potential defined on the whole sphere. Then this would be equal to the integral of the curl of the magnetic potential, which we just said was defined on the whole sphere, right? But then the thing is, if it's defined on the whole sphere, then you're within your rights to apply the divergence theorem, right? And so then you'd have the ball of radius r and the divergence of the curl of A. But what's the deal with the divergence of a curl? Search your heart. Find it to be empty. So it's 0, yeah. And these are hard to reconcile. So you see, it's inescapable that if we had a vector potential, there must be a defect in the domain. It cannot be defined for the whole sphere. It's impossible because of this. So anyway, this is the start of a much more interesting story about topology, but I'll just leave it there. So
You also have issues with the phi, right?
the what?
It's like whenever phi equals 0, there's also a discontinuity. So it's not differentiable.
Whenever phi is equal to 0. Which phi?
Well, on your A. When it jumps from 0 to 2 pi.
Oh, yes. That's a good point. Yeah, that's another sort of naked problem with this formula. Right. Good point. I think that happens, well, I guess you can make that happen wherever you want, but we probably want to make it happen at x equal to 0, so it's kind of the same place we already lost, but yeah, good point. At this point, I realize I've spent too much time on this. I'm going to skip the very physical example for the moment. Maybe I'll come back to it Monday. This is a nice gory example on page 245 to 246, but I don't have it. You got to know your limitations. So here's a question. Is, A physical? In other words, now, its curl is the magnetic field. Certainly the magnetic field is physical, right? The Lorentz force law says that in the presence of a magnetic field, the charge moves, right? V cross B. But what about A? Can A be physical? So some people, in other words, can be measured, right? Because the thing about A is it's not unique, right? Because we talked about last time that the curl of A is the curl of A plus any gradient of some function, right? So we could call this A prime. It's a gauge transformation. So they would both, they're equals. They both produce the same magnetic field. So can A be physical is the question. And the answer is actually provided to us outside of electrostatics, outside of magnetostatics. The answer actually comes from quantum mechanics. There's a couple of formulas I want to write, if I can find them. So these formulas from quantum mechanics. All right, and here's the formulas. I'll try to explain them. So a particle with an electric charge Q traveling around some path P with zero magnetic field B, but non-zero A. So, charge Q moving along path P, where B is equal to 0, but A is not equal to 0, right? Has phase shift. So we're talking about the wave function for the charge. Phi equal to Q over h bar, where that's Planck's constant divided by 2 pi, integral along the path of A dot, I guess we use dl in here, so I'll use that. All right. So it says, therefore, particles with the same start and end points but traveling 2 different routes will acquire a phase difference, delta phi, determined by the magnetic flux through the area between the paths and Stokes theorem. Let's see here if I can draw a picture maybe. So, all right, so how can we achieve this? Probably I should have done an example before this. We should have worked out what's the vector potential for a solenoid. Maybe we can still do that real quick. Famous last words. So a solenoid, right? Forgotten how to draw solenoids. I usually draw them loopy, but we got, let's say that the the current's going this way, all right? So, as you know, that produces a magnetic field like this, right? Right? And if the solenoid is, sufficiently long and so forth, the magnetic field inside the solenoid is, well, non-zero, but for all intents and purposes, the magnetic field outside the solenoid is what? You guys remember? 0, right? Or approaching that anyway. So you guys help me out. We want something, well, I don't know, we'll try. So the magnetic field is, if I remember right, mu naught Ni z hat, right? Where n is like the number density, the number per unit. You guys remember this from the first course? Yeah. So we would like to find a vector potential for this. B is equal to the curl of A for what A? Seems like we need to play the game we played earlier, but now for this formula, right? Or we could use your homework problem. Maybe we should use your homework problem. That'd be smarter. You guys are going to work it out anyway, right? So one of your homework problems was to work out the vector potential for a constant magnetic field. You're just supposed to show a certain formula works, right? And in particular, that formula was, I'm just hoping that the same homework problems are in my edition of Griffiths. See, mine look much cooler than, look, come on. This is the better Griffiths. Am I right? I'm right. Yours is stupid looking. I'm sorry, but you know, purple, really? Lame. Totally lame.
Would be not I, Y, X hat?
Ooh, I don't, maybe.
No.
Do you guys know which homework problem I'm talking about? Ah, here it is.
Y.
Problem 5, well, this one is 5.24. It says that if the magnetic field is uniform, you can say A of R, it won't be the same number, it'll be close to it. Minus 1/2. I didn't assign it?
I don't think so.
Oh man, why did I do that?
I missed something.
That's lame.
Yeah, let's do 5.24.
Well, but it's this problem, right? Yay,
That looks familiar.
yay.
Oh, that's 5.27.
Oh, 27, okay, but, all right, so, all right, anyway, that's minus 1/2 xyz, right? Cartesian product with, 0, 0, let's say b, right? This being b. What do we get? What did you tell me, Shane?
Well, for that curl, it would be minus YB over 2. XB over 2 is 0. I think.
All right, so let us remember that phi hat is like, cosine phi, my bad. Phi hat is minus sine phi, cosine phi, 0, yeah? Which is explicitly like minus y over s, x over s, 0. So we could rewrite this as s over 2 times b phi hat. Oh yeah. All right, sorry. There you go. That is the vector potential of the solenoid. I like that formula. That's nice. That's nice and cylindrically, right? See the S for cylindrical? Yes? All right. I know everyone's been gaslighting you to think that cylindrical is spelled with a C, but we know better. Anyway, so listen, as you can see, non-zero, right? I guess the question is that non-zero? Oh, this is everywhere, right? The thing is, this is everywhere. This formula here. Oh no, I can't say that. It's not everywhere. This is nonsense. My bad. This holds where? This would only be good for, I'm an idiot. This is for what? Context, yeah?
You have to find.
0 less than or equal to s, less than or equal to what? I mean, I didn't tell you yet, but let's suppose that this guy's got radius r, right? So the radius, this is inside the solenoid. Now, we haven't talked about this yet, but we really should talk about it perhaps today. What are the boundary conditions? How does the vector potential work? What's its deal? The deal is the vector potential is continuous, just like the potential was continuous. And so what that means is that outside of the solenoid, what's the vector potential outside the solenoid then? If you believe me about the continuity of A. The vector potential is constant outside the solenoid. Constant in terms of time, not in terms of... Ah, man, is that right? Oh, man, that feels... Well, anyway, I want to say just this, all right? Now, I'm a little bit skeptical in terms of what I just said, but I think it's okay. I'm going to suspend disbelief. It's constant outside the solenoid, and that's what the constant value is. We should probably prove the boundary conditions for A so we believe this more, right? But suppose it's right for a second. The picture then is this, guys. Here's the top-down picture, right? Here's the solenoid, right? B equals, B is equal to, B is not equal to 0 in here, right? Inside the solenoid. B is equal to 0 out here. And well, this is exactly the situation here, right? Of this theorem, that the phase, B equals to 0, but A not equal to 0. So B is equal to 0 outside of the solenoid. We're assuming the solenoid's very long, okay? And so the point is, if you take the path like this, or if you take the path like that, right, for some charge q, then you'd have phase change phi1 along this way. You'd have phase difference phi2 along that way. And it would depend on which path you took, because the A is not equal to 0 out here. But you could do more. You could say, well, this is actually equal to, well, there's more to say here if I have my head screwed on right. Blarg. If well, man. So the integral of A dot dl, right, is equal to the integral of the curl of A dot dA, right? Stokes' theorem. Right? But what is curl of A? So, I mean, I need to make clear what I'm talking about. So, let's say that this is on the boundary of S. All right, where S is this, here's B, solenoid, right? So this all together is S. So integral around the boundary of S, right, is by Stokes' theorem this, but that's the magnetic field, right? However, that's actually just equal to what? Mu naught Ni times pi r squared, right? Because that integral shrinks just to the solenoid, right? And so what that means is if you take a path that goes from here to here, right, P1 versus P2, notice that like P1, well, notice that P2 unioned with minus P1 is the boundary of S. See, S is like this, right? So P2 is the right way, P1 is the wrong way. So the boundary, positive oriented boundary of S is like this. The magnetic field's coming out of the board at us, okay? So what that all means then is that this is equal to the integral along P2 of A dot dl minus the integral along P1 of A dot dl, right? And so what that shows you then is that the integral, so this then, if you believe what I wrote over there, is the change in the phi, change in the phase. So you can measure the change in phase. The change in phase between those two paths has to be related to the magnetic field that flows in the area of the solenoid like that. But that nevertheless is a measurable thing that's based on the non-zero vector potential. So in quantum mechanics, yeah, we can see a physical effect of the vector potential. It must be, then, that this physical effect is independent of this ambiguity, right? Because physics doesn't allow for multiple outcomes for a given experiment, because we're not in quantum mechanics yet, right? So, oh, wait a minute. Well, nothing to see here. Let's go on. This is called the Aharonov-Bohm effect. Similar mathematics shows that if there exists a single magnetic monopole, even one, it implies the conservation of charge. Excuse me, not just the conservation of charge, the quantization of charge, rather. That all charge has to come in multiples of a fundamental charge. And this is what we observe. Every single charge that's observed is a multiple of the electron charge.
Didn't we have a rule that said no magnetic monopoles?
We do.
So is that not true?
I don't know. All charge is quantized. That seems to suggest there's a magnetic monopole out there somewhere. I mean, this is a standing question of current physics. This is why a lot of people are on the side of there's a magnetic monopole somewhere or somehow or, you know, it's in your room. It's in your room. Thank you, Shane. Very helpful. Anyway, oh, by the way, credits where credit's due. The Aharonov-Bohm effect brought to you by Wikipedia, because I don't have a quantum mechanics book in my office at the moment. But and neither does KK. I checked his office, and I'm not going to walk all the way down to Dr. Budara's. You know, it's too far. So if that's okay with you guys. So the last thing for today is probably to talk about boundary conditions. And so he has this, you know, wonderful picture of the formulas, and I guess I'll write that out. I probably shouldn't. Oh well. So to get from here to here, we do this formula. Right? To get from here to here, we were up against that. We talked about it a little bit last time. The Laplacian of A is minus mu naught times J, right? So this vector of Poisson equations. To get from here to here, of course, we've got B is equal to the curl of A, right? Well, all right. Well, he's tacked on the divergence of A is equal to 0. I'm not, I don't know what this diagram means sometimes. Anyway, and of course, to get from here to here, Biot-Savart, right? B mu naught over 4 pi integral of J cross script R over script R squared d tau. And the other way, I suppose, oh well, anyway, the other way is like Ampere's law. Sorry, I should have made this picture way bigger, right? And of course, you've got the divergence. We're back to no monopoles again, all right? We do assume no monopoles in here, by the way, until we don't. So, now this, of course, is not boundary conditions, but let's think about a surface, all right? And suppose you've got surface current K. So if you were to draw, a little box, right, above and below, you could calculate that, of course, you know that the divergence of B is equal to 0, which means that the magnetic flux is equal to 0, right? So if we think about, what that suggests then is that the perpendicular part above minus the perpendicular part below times A, right, is equal to 0. So supposing this has like, not the vector potential, but the area of the little box, all right? Notice that, why is there no flux on the edge? I mean, even if, setting aside symmetry even, if you just make it very, very thin, right, there can't be flux through the ends. They have to just be through the top and bottom. So because the divergence is 0, we get that the perpendicular components above and below have to be equal. All right. Now, on the flip side, if we look at the surface like this, all right, and we look at like a little loop like that, oh man, brain not working all of a sudden. Yeah, I'm sorry, I need to, wrong picture. Let's make the loop. Let me use my already existing picture up here. So think about an Amperian loop like this, right? So here's where it intersects the thing. So if you look at that, we have the integral of B dot dl is equal to, well, mu naught times I enclosed, right? So let's let the length of it be L above and L below, right? Again, pinch the loop down, pinch it. So it only picks up the above and below, but this time let's see here. I'll make it go this way up here and that way back there, all right? That way the current's going the positive sense through without being... Anyway, the point is, I get listen to me, B parallel above minus B parallel below times L, right? That gives me the circulation because the vertical pieces don't give me anything, right? Notice the hand waving. So that gives me mu naught. What's the current enclosed through this Amperian loop?
Okay.
K.
Okay.
LK. Yeah, LK. So apparently, B parallel above minus B parallel below is equal to K, mu naught K. Right? And Griffiths points out that we can sort of vectorize these results by simply writing that the magnetic field above minus the magnetic field below is equal to mu naught times K crossed n hat, where n hat, of course, is the normal to the surface. Does that make sense? Let's see if we can verify that. Like, so K is going this way, and K is going this way, n hat's going out. I'm saying this way is the way in which the that's defining positive sense of parallel, which is what I was, positive sense of parallel like that, just like I'm saying. So it does comport with this in terms of the directionality like I'm claiming. On the other hand, we just have A above is equal to A below. He claims that. He says the divergence of A guarantees that the normal component is continuous. And let's see here. Let's try to understand why why is this true? Yeah. What do you guys think? I think it's very much related to the calculation we just did for the Aharonov-Bohm, which I've erased. So, like, if so if I have this, well, anyway, I'm already, tell you what, I'll start here next time. We'll prove the continuity of A and start next class. I'm already over time, so I'll stop here. It's good enough place to stop. So thank you for your patience. I do appreciate it.